All right. So for those of you who aren't here, make sure you review Arrhenius definition of acids. Make sure you review your naming. Okay, for everyone, we're moving on to strong versus weak acids. Now, when you think of a strong acid, you might think of an acid that has a very low pH, like a 1 or 2 pH sample. But really, strong versus weak is its own different category. Okay? A strong acid completely dissociates in water. Dissociation is that term we learned for like when the ions separate. A weak acid only partially dissociates. Really the difference, what it comes down to is certain of the anions hold onto the hydrogens a lot stronger than others. So it's kind of counterintuitive. The strongest anions, for example, fluorine. We didn't really go too much into properties of the elements, but fluorine is pretty much the strongest element when it comes to holding electrons because it wants one and they're so close to the nucleus. And because fluorine is so strong, it's actually a weak acid because it holds its hydrogen so closely that only some of it dissociates. Whereas iodine is a very weak anion. I mean, that's why, like, if you have fluorine, it's like explosive and it's going to kill you. Whereas, anyone know what they use iodine for? Like, if you give blood or something?
If you go to, like, the doctor, they use, like, clean up where your wound goes or whatever.
Yeah. And, like, if you give blood, they basically rub liquid iodine in your arm to kind of disinfect it before they, put the needle in. So iodine is very weak in terms of what it reacts with, and that's why iodine or hydroiodic acid is such a strong acid. Because iodine is weak, therefore when you mix it in water, the water basically plucks all the hydrogens off of it. So let's go through some examples. Let me put it this way. Strong acids. HCl aqueous, hydrochloric acid, is a strong acid. And the way we write sort of the formula for the dissociation of this, which by the way means it splits into an H plus and a Cl minus, is we add the water, and it's going to be liquid. Very rarely do we use the liquid symbol, so what do I write for that? For liquid? Yeah, it's the script L, so like a little loop. And basically the HCl is going to break up, and where's the H plus going to go?
The H2O.
Good, it's going to go with the H2O, forming H3O plus.
This is an example of strong acid, right?
Yes, HCl is a strong acid. Okay, so once that happens, what am I left with? After the H leaves, nothing happens to the Cl, so what am I going to write here? Cl minus. And it's important, if it were just Cl, it would because chlorine's a Brinkerhoff, it would find another chlorine and latch together, Cl2. But since it is in its ionic form, it's just going to be Cl minus. And these are going to be aqueous. Because this is a strong acid, this line is going to be solid in one direction. Okay? For a weak acid, such as, I think I gave hydroiodic acid as an example before. Let me double check that. Sorry, that is another strong acid. Weak acid is hydrofluoric. And again, for the reason I said before, fluorine is a really strong anion, so it's not just gonna let the water pull all the hydrogens off. So HF aqueous, that's hydrofluoric acid, plus liquid water, And instead of just an arrow, we do this. One arrow this way, one arrow that way. H3O plus aqueous plus F minus aqueous. What this means is, yes, a lot of this HF is going to dissociate into hydronium plus fluorine, but some of that is going to basically go back into water. It kind of happens in equilibrium. So all of your strongs are going to have the solid line going to the right. All of your weaks are going to have the double lines or double arrows. Yep.
Do Brinkelhoffs not matter with these?
They don't matter with these because Brinkelhoffs really only apply when the element like stays together like with its electrons. Like if you bump chlorine out in a single replacement reaction, you have to do Cl2. But if it's an ion, no. So Brinkelhoff doesn't apply. I don't do F2. Yep.
Does it matter with the arrows which if it, like the top is pointing right or if it's pointing left? No.
Doesn't matter, but I've always seen it written this way. And as long as you show it can go in both directions. So weak acids, you draw this arrow. Strong, you draw that arrow. Okay. Let's list the rest of the strong and weak acids. I'm not going to have you guys memorize these, at least not for now. But it is good to know. So make a chart in your notes. Strong acids. Hydrochloric acid. Hydrobromic acid. Hydroiodic acid. Sulfuric acid, by the way, all these are aqueous. And nitric acid. Weak acids are basically the other ones of the 10. So hydrofluoric acid, phosphoric acid, acetic acid, and carbonic acid. Am I forgetting one? Yes, hydrosulfuric acid as well. All right. And again, all of these are aqueous. So again, when we use the term strong and weak, it doesn't really matter. It doesn't actually mean the strength of the acid in terms of its pH. Or like, we've used 1 molar HCl, we've used 6 molar HCl. You can definitely say in the context of lab, this is really strong acid, be careful because it's 6. But you couldn't then say, well, 1 molar is a weak acid because all HCl is a strong acid. You would just say, I mean, we use the term strong and weak in the everyday sense, but if you want to say a strong acid, it's those 5, weak acids are those 5. There's obviously hundreds of more acids, these are just the common ones. Alright, so we've covered Arrhenius definition, we've covered naming, we've talked about hydrogen ions. What we're going to do now is talk about the next definition for acids, which is Bronsted with a line through the O, it's Danish. Bronsted-Lowry. Bronsted was a Danish scientist, Lowry was an English scientist. They independently and at the same time came up with this theory. So instead of, picking one, we decided to name both of them. We'll pull up a quick video on this.
The Arrhenius theory of acids and bases
Start it up.
defines an acid as a substance that releases protons in solution, and a base as a substance that releases hydroxide ions in solution. We know that ammonia can act as a base and exhibits alkaline properties, but contains no hydroxide ions. How is this possible? In this lesson, we will learn about the Bronsted-Lowry theory of acids and bases, which fills in the gaps in the Arrhenius theory. You have learned that acids are substances with a pH lower than 7. We can test for acids using universal indicator solution, or paper, which turns red or orange, all depending on the strength of the acid. Blue litmus paper also turns red in the presence of an acid. An example of an acid that you are likely familiar with is hydrochloric acid. Hydrogen chloride dissolves in water to give hydrochloric acid. Hydrogen chloride will dissociate to give a proton and a chloride ion. The proton is not just released, but it is transferred to another substance. For our example, water accepts the proton to form a hydronium ion. A hydronium ion is also known as an oxonium ion. A Bronsted-Lowry acid is a substance that releases or donates protons in solution, in our case, hydrogen chloride. A Bronsted-Lowry base is a substance that accepts protons in solutions, in our case, water. Notice that the definition of a Bronsted-Lowry acid or base is not a function of pH. So an acid-base reaction, according to the Bronsted-Lowry theory, involves the transfer of a proton from one substance to another. In the introduction, we mentioned that ammonia acts as a base even though it does not release hydroxide ions, which is stipulated in the Arrhenius theory. When ammonia dissolves in water, it accepts a proton from water. Notice that this reaction also involves a proton transfer. Can you figure out which substance is acting as an acid in this example? Which is acting as a base? Please pause the lesson to think.
By the Bronsted-Lowry definition, the thing that donates a proton or an H plus is the acid. So can someone look up there and tell me which of those two reactants is donating a proton? It's H2O, Sal. Why? What does the H2O turn into? Right. Notice an H plus is being plucked from the H2O and it's going onto the NH3, creating ammonium and hydroxide. So which is acting as the base? NH3.
Oh.
The base is just the thing that accepts the proton. So water donates a proton, water acts as an acid. NH3 accepts that proton, so in this example, NH3 is the base.
About this and resume when you are ready. In this example, water acts as a Bronsted-Lowry acid because it releases a proton. Ammonia acts as a Bronsted-Lowry base because it accepts a proton. So a base, according to the Bronsted-Lowry theory, does not need to have a pH greater than 7, or turn red litmus paper blue, or turn universal indicator solution or paper blue or purple. The only requirement is that it is able to accept protons. Have you noticed that water acted as a base in our first example, but as an acid in the second example? Substances that can act as either an acid or a base are amphoteric. In conclusion, according to the Bronsted-Lowry theory, an acid is a substance that dissociates to release or donate protons. A Bronsted-Lowry base is a substance that accepts protons. Therefore, an acid-base reaction, according to this theory, involves the transfer of a proton.
Otter, can you hit the light, please? Excuse me. All right. So, by the Bronsted-Lowry definition, an acid is a proton donor use the term donor, but it's not like it has a conscious. It's something that releases protons onto something else. And a Bronsted-Lowry base is a proton acceptor. And as the video said, this kind of filled in some of the holes. Because people have known certain things are acidic or basic for thousands of years. They just didn't have the terms acid or base. And after Arrhenius, people said, well, things such as NH3, they act like a base, but there's no hydroxide there. So this is the definition we came up with. You guys can take out this packet we started working through yesterday, called Acids and Bases, and turn to the second page, please. So looking here, we have Model 2, the Bronsted-Lowry acids and bases. HCl aqueous plus water yields H3O plus aqueous plus Cl minus aqueous. This is reaction number 1. And this is what we already talked about for an example of a strong acid. So in this example up here, what is donating a proton? Right?
The HCl.
Right. It's donating a proton. So a proton, also known as an H plus, is being pulled off the HCl. And where is this being dumped onto, Ryan?
H2O.
Right. Okay. So therefore, when you pull an H plus off this, it turns into Cl minus. When you add an H plus to this, it turns into H3O plus. It's important to note the charges here. If it pulled a hydrogen atom off of the HCl, you would be left with chlorine by itself, and you would get H3O without a charge. But because it pulls a proton or an H plus off, now HCl becomes Cl minus, H2O becomes H3O plus. Don't forget the charges. Okay, the next example it gives is NH3 aqueous plus HF aqueous yields, well, we could probably figure this out. In this case, this acts as your acid. It's kind of labeled for you, but you could also figure this out, right? What type of acid is this? Hydrochloric acid. So as a Bronsted-Lowry acid, what is this going to do?
Release protons.
Right, and specifically one proton. This is going to donate its proton to this, so that becomes our Bronsted-Lowry base. So what is the HF going to turn into after it loses its H plus? Danielle?
F minus.
Good. And that is, of course, aqueous. And Ryan, can you tell me what the NH3 is going to turn into after we dump the proton onto it? With a charge of plus. Because look, it was neutral before. It had no charge. We add an H plus to it. Now it has a plus charge. All right, reaction 3. I like this one because it takes the product and it says, well, what if we mix that in water? NH4 plus aqueous plus H2O liquid. Noticing something I don't really like about this. It gave, in example 1, it gave the both arrows left and right. Probably shouldn't have done that. Question? Yes. In this one, it is forming, and I believe this is a weak acid, so we'll go both ways. NH3 aqueous plus H3O plus aqueous. So in order to get here, which one of these two acted as my Bronsted-Lowry acid by donating a proton? Danielle.
Ammonium.
Good. Ammonium gave up a proton. So if I'm going to pull an H plus off of this, it turns into NH3. And the proton gets dumped onto the water, turning the H2O into H3O plus. So again, this acts as my Bronsted-Lowry acid, my Bronsted-Lowry base. Fourth example is F minus aqueous plus H2PO4 minus aqueous, which isn't really a polyatomic. This is kind of like it's a phosphoric acid that has undergone a little bit of ionization, meaning it gave up one of its hydrogens already. This is going to turn into HPO4 2 minus aqueous plus HF aqueous. So let's look at what happened here. Which of those first two terms gave up the proton, Ryan?
The H2PO4.
Right? So this gave up the proton, so if we're going to pull an H plus off of this and give it to the F minus, now we can see where the Bronsted-Lowry base comes into play. F minus acts as our Bronsted-Lowry base because it accepted the proton, turning it into HF. Okay? Any questions about this? Alright, so with this sort of background information, go ahead and complete 7 through 10 on this packet. If anyone needs another copy, let me know.
Mr. Curran back.